So in general, when we say radiation, we mean we are moving energy around between things that are not actively touching one another. The kind of radiation that we're going to be concerned with in the rest of this class is actually just light. So light is radiation with photons. So we've talked about some induction in the past couple of weeks. So we've noticed that you can create a voltage with a changing magnetic field. You can create a magnetic field with a steady current, but there's a more general relationship. And your book does a really good job at dancing around it. So section 24.1, Maxwell's equations, electromagnetic waves. Notice even though the section is called Maxwell's equations, the book doesn't actually write down Maxwell's equations anywhere. It gives a qualitative explanation of what they mean. Right? So they say electric field lines originate on positive charges and terminate on negative charges. The electric field is defined, blah, 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 blah. Why is it that the book goes through such lengths to describe Maxwell's equations without actually writing down the equations? Anyone have a guess?
I think I remember it saying stuff about like it requiring calculus, and so it would rather not explain it to you.
Yes, that's exactly right. So Maxwell's equations are sufficiently precise that you can't even write them down without a calculus background. So in Maxwell's equations relate electric magnetic fields, but not the strength of the fields. It relates the rate of change of electric fields in space and time to the rate of change of magnetic fields in space and time. And if you are talking about rates of change, you are definitely in calculus territory. To make it a little more complicated, even if you've had calculus 1 and you sort of understand what a derivative is, that it's a rate of change, when you start talking about the rates of change of vectors, there are actually two different kinds of derivatives you can define for a vector. So the two kinds of derivatives, if you try to describe them without calculus, they kind of sound silly. So one kind of derivative of a vector is called the gradient, and one is called the curl. So the gradient of a vector just describes in which direction it increases or decreases the fastest. That is, it talks about the size of the function that you're taking the derivative of. And the curl describes how swirly the, the field is. And without knowing some calculus, really swirly is the best that you can say about it. So your book bends over backwards to not write down the equations, even though they're actually quite simple and elegant. But just because they're easy to write down doesn't mean they're easy to explain. So we're going to take the book's path, and we are not going to think too hard about the specifics of Maxwell's equations. What we will say uh, is that a changing electric field causes a B field, and a changing B field causes an electric field. It turns out that light, these photons, that at their core, what light is a set of matched electric and magnetic fields that are oscillating together. So let me pull up a picture, actually.
Is the x multiplication?
The x is sort of multiplication. It's a kind of multiplication called the cross product. It is not a 2. So we will get back to dealing with Maxwell's equations directly after you've had 3 semesters of calculus. But here's the idea behind light. So if we call these, say, the x, y, and z directions, and these are arbitrary, of course, we say the electric field is oscillating in the y direction. And because the electric field is oscillating in the y direction, that causes an oscillation of the magnetic field in the z direction. And because the magnetic field is oscillating in the z direction, that causes an oscillation of the electric field in the y direction. So the two of these fields put together feed into each other, and they're self-sustaining. And it took us a very long time, but this turns out is our best idea of what light even is, actually. Okay. So the electric field has a direction, it's a vector. The magnetic field has a direction, it's also a vector. The direction that light is moving, right, is, you might have some right-hand rule action going on. So if you point your thumb in the direction of the E field, right? Or other way around. Point your thumb in the direction of the B field. Sorry. Wow. I need another cup of coffee. Your fingers in the direction of the E field, your palm in the direction of the B field, your thumb points in the direction that the light appears to be moving. And this direction, I kid you not, is called the pointing vector. Pointing is actually a dead physicist. But it's also funny because that's the direction that the light points in. So sometimes you have these little bits of kismet in science history. So light sustaining itself through oscillating electric and magnetic fields is all well and good. But how do we make those electromagnetic waves? Well, we use transmitters. Right? So a transmitter is just some shape of wire that we run alternating current through. So as if we run current through it this way, then we will make a B field that's into the page through the loop. And as our alternating current reverses direction and ends up coming back the other way, we will end up making a B field that's out of the page. And the change between them, right? So the rapid change in B field is what causes electromagnetic radiation, right? We're making an oscillating B field. That oscillating B field makes an E field to match, and off goes our photon. We've gotten really good at making transmitters, and all of our modern communications are built on them. So the radio, of course, is built on transmitters and receivers. Your cell phone communicates to the nearest cell phone tower because it has a little transmitter in it. If you're on a laptop right now using Wi-Fi, there's also a transmitter in your laptop that communicates with the Wi-Fi hub that you are connected to. On your laptop, your transmitter is usually a wire that's built into the edge of your screen. So this picture I've drawn of a transmitter here is basically what the transmitter in your laptop looks like. For cell phones, we have to be a lot more clever. They have a little chip that's called a fractal transmitter. And they're very clever, they're very complicated, and we definitely won't be talking about them in this class. Just, they're a thing. We've had, close to 150 years at this point to work on transmitter design, and it's something we as a species have gotten really good at. The other really cool thing to come out of this discussion in the first half of chapter 24 has to do with this permittivity and permeability that we've had to attach to our attach to our equations. Turns out that these numbers are not accidents. And because of the intimate way that electric fields and magnetic fields are related to light, if we multiply these two numbers together, take the square root. This is the speed of light. So this permittivity and permeability, they are not independent of one another. They are tied to a more fundamental constant of the universe. Alright, so that is 24.1, 24.2. There's not a lot of meat, I would say, in chapter 24, but it is a conceptual background that we need to get through before we can talk about light in more interesting ways. All right. Many of you, I'm sure, have seen something like the image that I'm pasting into the workbook now. If you recall from our discussion of waves, there is a definite relationship between the speed of a wave, its frequency, and its wavelength. Right? So in general, the speed of a wave is equal to its wavelength times its frequency, and this is true for light as well, which is made of electric field waves and electric fields and magnetic fields. The product of the wavelength and frequency of the light is also equal to the speed of light. So when we talk about wavelength, we're literally talking about the physical distance between peaks, right? So the distance between peaks in the electric field or peaks in the magnetic field, those are going to be the same distance, and that defines the wavelength of the light. Alright, so our eyes are optimized to really only see colors in a pretty narrow band, just right in here. Anyone want to take a guess as to why our eyes evolved only to see these wavelengths of light? Anthony, you are on the right track, my man. Those just happen to be the most common colors that our sun emits. So if you live on the surface, your environment is bathed primarily in these wavelengths of light. And so there's a definite evolutionary advantage to being able to perceive the behavior of these wavelengths of light. So yes, the sun also creates quite a bit of UV and IR light, but UV light is energetic enough, has enough energy to damage cells. So actually a good survival strategy is to minimize your exposure to UV light at all, whether or not you could use it to see. Now, some animals do actually use UV light to see. Honeybees and mantis shrimp, two of the most badass creatures on the planet, can see in ultraviolet. In infrared, there's a different different constraint, right? The longer if you have, wavelengths of light that are 10 to the minus 4 meters, right? That's 0.1 millimeters, right? You need a receptor about the same size as the wavelength of light you are trying to see. So if we wanted to be able to see infrared light, we would need structures in our eyes that are about zero point 0.1 millimeters large, and that is too big for the constraints that we evolved under.
Our eyes would need to be bigger in order to house that size of structure in our eyes to be able to see in infrared.
Yeah, that's
Right.
that's essentially correct. So the rods and cones in our eye are of the order of hundreds of nanometers in size, because that's the size of the light that they are trying to detect. Right? You would need structures that are 1,000 times bigger than rods and cones. So you either need much larger eyes to fit in the same number of these structures, or you go with fewer of the structures and you sacrifice resolution. So on our own path, we just forewent IR altogether, and we went with higher resolution visible light range. What structures in a video camera allow it to see in infrared? That is a really excellent question. So it has, so a video camera actually uses a charge-coupled device to record light. So instead of using like physical structures and diffraction, like our eyes do, they operate on a, or at least modern cameras operate on a direct absorption principle. So they're using quantum mechanics to get thin layers of material that actually directly absorb the kinds of photons that they are interested in detecting. And I know that doesn't, it's not a very satisfying answer. Just say it's quantum mechanics, woo! But I mean, it is quantum mechanics. So you can, once you know some quantum mechanics, it's actually pretty easy to engineer a material or a thin film of material that will absorb very particular wavelengths of light. Okay. On a slightly different note, so all of these kinds of radiation, they're all light. They're all photons. They're all coupled electric fields and magnetic fields. But in practice, how we make these is very different. So if we want to make radio waves, we use a transmitter with AC current to wiggle a wave into existence. Infrared light is mostly a molecular phenomenon. So you may remember from chemistry that electrons actually prefer to live in very specific spots in an atom, and they're not just anywhere. Like electrons only take on certain amounts, certain energy levels. Right? Did everyone get that in Chem 2? I do not see any reassurance in chat that you did actually get that in Chem 2.
I might have, I just don't recall at this point in time.
So yeah, electrons reside in specific orbitals, and every orbital has a certain energy associated with it. So electrons don't just have any amount of energy, they can only have specific amounts of energy. So if we have, so an orbital diagram usually looks something like this, right? And the difference in this, on the y-axis is energy. Electrons can move between these energy levels, but they can't stay in between the energy levels. So an electron that is up here could go down here. And in fact, electrons prefer to be in as low an energy state as possible, and in general, nature prefers low energy organizations as much as possible. When an electron does this, the way that we conserve energy is a photon gets emitted. So all of the energy that an electron would have to give up from going from a higher level to a lower level, that energy is sent off as a photon. And when it's electrons doing this transferring, the energy difference between levels is usually in the UV range. So to make UV light, you have to somehow get electrons into a higher than normal state, and then wait for them to relax down to their ground state, and when they relax back down, they'll give off UV light. For IR, in the IR spectrum, we play the same game, except instead of electrons going from one energy level to another, it's actually the vibrations of molecules. So molecules are a little bit more complicated than atoms. But the atoms in a molecule can vibrate in specific ways. And when they go from one vibrational level to another and there's a difference in energy, that difference in energy gets carried away by a photon, and that is typically an infrared amount of energy. So essentially, UV and IR light are both mostly made from chemistry. X-rays are a little bit more energetic. And there's definitely more than one way to get X-rays. You can get X-rays from nuclear chemistry. You can sometimes even get X-rays from regular chemistry. But if you go to the doctor, the way they make the X-rays in your X-ray machine is like this. There's a filament, usually made of tungsten, just like an old-fashioned incandescent light bulb. They get this hot in some way, usually by running electricity through it. When you get tungsten really hot, its top couple of valence electrons just kind of boil right off. Its valence electrons are attached weakly enough that you can just boil the electrons off of the tungsten. The tip of this filament is actually inside what is essentially a large capacitor with a large voltage across it. This large voltage accelerates your electrons and they get super fast, like a several percent of the speed of light fast, and then they slam into the other side of this thing. So they slam into this plate, which is also usually made of tungsten, but can be made of other things. And a similar game to the UV light gets played, except because you're slamming these hugely fast electrons into the material, the electrons that are in the tungsten on your target there, they get excited super high up. They go many energy levels up. And when they drop back down, the energy gets carried away as a photon, but it's a lot of energy. So you get an X-ray. There's a fancy name for this sort of X-ray production too. It's called Bremsstrahlung. Clearly, it was a German who invented this this technique. Okay. Have I completely lost people at this point, or are you still with me? Okay. So chapter 24 is all conceptual, basically. There's not. I mean, there are a few kinds of calculations that the book presents, like how to calculate the intensity of energy in a wave of light, how to calculate, frequency and wavelength. But I mean that's it basically. So what I propose is that we take a short break. Take 10, grab a coffee, a water, a leg stretch. It's 12:50 by my clock right now. So at 1 o'clock, we will come back and we will dive into a more concrete application, which is chapter 25.